Hello, my name is Lallawmsangi. Today, my poster presentation will be on chemoselective reduction of dicarboxylic acids via iridium catalyzed hydrosilylation. And the main thing is that we want to synthesize an aldehyde compound which has a wide variety of application in biology, and it has in the fragrance industry and it has a lot of industrial applications like the production of resin, adhesive, and textile. So previously, um, a study has been done for the reduction of an aldehyde using diol from an ester, but this reducing agent is hazardous, air and moisture sensitive, and it has a strict reaction conditions, and it is not suitable for a wide range of functional groups. So, and also that the desired product aldehyde is very reactive towards diol, so it can lead to over reduction and can avoid alcohol. So we want to see a better way to afford an aldehyde. So previously, the efficiency of this iridium catalyst was reported, and it was established to study the controlled reduction of an ester to silyl acetal, which upon hydrolysis can afford this aldehyde. This iridium catalyzed hydrosilylation is a mild reaction condition, and it is a simple product isolation, and it can tolerate many functional groups, unlike diol. So when let's address the chemoselectivity. Previously, ketone, ester, and amide has been reported to uh, afford hydrosilylation of carbonyl containing substrates, and ketones and esters undergo hydrosilylation to attain a quantitative and a conversion in 0.3 hours at room temperature, while an dimethyl acetamide is slowly hydrosilylated. So this was already reported, which is a singly monocarbonyl compound was already reported. But here we are proposing to study the chemoselective iridium catalyzed hydrosilylation, and this is a need to be explored for dicarboxylic acid compounds. So we want to see if iridium catalyzed hydrosilylation can differentiate between two carbonyls, whether it can chemoselectively hydrosilylate one carbonyl over the other. And this is our model system. Now, this is chiral auxiliary compound react with catalyst and silane. In the presence of solvent, we get the acetal hydrosilylation, and upon workup, we will get the aldehyde. And the parameters that we're going to use is iridium catalyst, silane, solvent, temperature, and time. And analytical methods that we use are protein 13 carbon NMR and GCMS and FTIR. And now, firstly, we have done the optimization of N-acetyl acetal, and we screened iridium chloride, iridium metals in presence of THF and DCM in various temperature, like room temperature and 40 degrees Celsius. So we can see that iridium methoxy and in presence of DCM at 40 degrees Celsius affords 97% yield in 40 minutes with 10-1 DR. And next, we screen the silanes. So for this reduction of the dicarboxylic acid amides, um, uh, the several silanes were screened. So we concluded that dihydrosilane proves to be most effective, and the hydrosilylation of the carbonyl double bond took place at 40 degrees Celsius. And these are the substrate scope they have done. So we can see that it is applicable to different kinds of substrates and gives a high amount of yield. And these are the isolation parts. So after hydrosilylation of its substrate studied, we have done the workup. So for low molecular weight, Brady's region was used to trap the aldehyde, and for high molecular weight, acidic workup was used to afford aldehyde. And to conclude, that simple, highly efficient method was used for selective reduction of dicarboxylic amides, and this catalyst is highly active, long-lived, and we discovered this catalyst to be most effective, which we have optimized the reaction condition for chiral auxiliary, and the reduction exhibit a good yield. These are things that we have studied so far. Thank you very much for your attention.